company. It's more about the company than it is about the software. So we want the company name MathWorks to, everybody knows about MATLAB, but people don't know about MathWorks, the company. So us supporting public radio is one of our major both philanthropic and marketing endeavors.
Welcome, everybody. Welcome to the first of the 2017-2018 Distinguished Lecture Series here at the Scientific Computing and Imaging Institute. I'm Chris Johnson. I direct the Institute, and today we're very happy to have Cleve Moeller be our first speaker of this year's lecture series. So I think it's maybe obvious that people know who he is because we have so many people here. I'm sorry that we didn't get a larger venue, a little more popular than I thought. So because you all know that Cleve is the inventor of MATLAB and the co-founder of MathWorks, maybe a few things that you might not know, at least some of you, is that Cleve was born at LDS Hospital in the Avenues and grew up here in Salt Lake City. He graduated from East High School, just a few blocks away from the University of Utah, and he was one of the first employees of the university's computer center.
I'm going to talk about that.
All right. After he left Salt Lake City, he headed to Caltech for an undergraduate, and then at Stanford.
You're giving my talk here.
I'm giving your talk. All right. Okay. Can I say who your office mate was at Michigan?
Yes.
All right. So his first faculty position was at the University of Michigan, and his office mate there was Professor Frank Stenger, who is sitting right back there. And so it's a small world. And Cleve will tell you a little bit more about it. So please join me in welcoming Cleve Moeller.
Thank you. The part about Frank Stenger wasn't in my talk, so that's thank you for that little tidbit. It's a pleasure to be back here. As Chris said, I'm from Salt Lake. I left here 60 years ago exactly, right after summer job, and then went off to Caltech in the fall of 1957. And my father was eventually editor of the paper in Ogden, so I came back to the area here a few times, but I don't have any. The only family I have left here is you guys. Then the new people I met here, Frank and Nelson Beebe. Let me tell you about the evolution of MATLAB. I want to go clear back to this period I'm talking about, even before, and talk about how I got involved in this business. I want to talk about three men who were very important in my life: John Todd, George Forsyth, and J.H. Wilkinson. But the story begins with Alan Turing, famous for breaking the German codes in the Second World War. After that, he went to the National Physical Laboratory, where he proposed building a computer called the ACE, the Automatic Computing Engine. It was too complicated. It was based on work he'd done in secret during the war, but he couldn't tell his management about it. So they decided not to build it. It fell to an assistant of his named Jim Wilkinson, and to lead a group that produced a simplified version of the machine called the Pilot Ace. Wilkinson built the arithmetic unit. Here he is at the console of the Pilot Ace. He went on to become the world's leading authority on matrix computation, excuse me, and was a friend and mentor of mine. At the same time in Southern California, the National Bureau of Standards was sponsoring the development of a American computer called the Standards Western Automatic Computer, SWAC. They gathered a group of mathematicians here at something called the Institute for Numerical Analysis. That's George Forsyth, and the tallest guy in the center. Olga Towsky Todd was the only woman in the group, and her husband, John Todd, is looking over her shoulder. This institute was dissolved in 1955 in a big political controversy involving McCarthyism and battery additives that I'll tell you about sometime. And these people dispersed to universities around the world. Forsyth went north to Stanford, and the Todds went across town to Pasadena and Caltech. Here's a picture of the math faculty at Caltech in the late 50s. Olga Towsky was the first female full professor at Caltech. And again, John Todd is in the back row looking over his shoulder. So Orley sent this around. How many people saw this in their email? Okay. So Orley sent this around to a few people. Here's a clipping out of the Deseret News in the spring of 1957. Is the Deseret News still exist? Well, you're not sure about newspapers. So they wrote articles about precocious high school students. And this says, I'm going away to Caltech, and there's electrons whirling about my head. I think I got admitted to Caltech because I was from Utah, and that was their idea of diversity back then. At Caltech, I took numerical analysis from John Todd, and we used this computer, the Burroughs 205 Datatron. It was one of only a handful of computers in Southern California at the time. But I want to diverge from my usual talk and tell you and show you, I write a blog called Cleve's Corner, and this is, where is it? This is a blog that oh, come on. Why doesn't that open up? I shouldn't diverge from the regular talk. I have a tremor. I'm talking to Chris about it tomorrow. Here's I have trouble clicking on these things. Okay, so this is a draft of the blog that's coming up about this computer. Now I want to tell you about it because I used it at Caltech, and I also used it here. This is University of Utah's first computer, and I worked here as a summer job in 1960. There was a woman who managed this. There were three people in the center, a woman who managed it, me, and a gal who ran the key, four, and a gal who ran the did key punching, and a guy named Joe, who was a graduate student that maintained the computer. Anybody have any idea who that was? I'd like to find him again. Anyway, so the woman quit, and for the summer of 1960, I was the acting director of the University of Utah Computer Center. And we ran this computer. We have flashing lights here. It was in lots of movies. It's a room full of computer. Those cabinets in the background contained vacuum tubes. How many people know what a vacuum tube is? How many people have ever held one? Okay, so here they are. Here's vacuum tubes. And this is one digit in the register of that machine. It's a decimal machine, but there are 4 tubes there, and they use just the 0 through 9 out of the 16 states. If you ever saw any binary combination higher than that, it was an error. So here's an old machine that somehow been in an old warehouse. You see the racks of tubes there. There were about 3,000 of these tubes. Machine cost $5 million in back then. And then down here on the right, there's a drum. The big deal about computing back then was, what are you going to use for memory? This was before transistors, before core, and this memory was a drum. The drum had 4,000, could hold 4,000 words, 4,000 10-digit words. And they were arranged in 20 bands of 200 each around the drum. And then there was a special band that took 20 words and repeated it 10 times around the drum. So the access time on that was 10 times faster than the regular memory. You could think of that as a cache. Anyway, there's the drum down in the corner. We punched our programs in absolute numeric, we wrote our programs in numeric machine language and punched them on paper tape. Here's a program for that machine out of the manual at the time, and you can see individual machine instructions there written down, but we didn't have an assembler. We couldn't punch them in like that. We had to convert those to numbers and actually just put them on the numbers. There's 20 words, there's 20 instructions there, and this would fit in the fast loop, so you could run this thing fast. I wrote a program while I was here that fit exactly in 20 words, but it didn't have a way to escape. And I couldn't get out of the infinite loop. I needed a skip on minus instruction. And I asked Joe, and Joe disappeared behind those cabinets with a soldering iron and blueprints and put in a skip on minus instruction. He says, the opcode will be 51. So I put that on my tape. We had the only, University of Utah had the only Burroughs 205 in the world that had a skip on minus instruction. Anyway, so that's a diversion there. I don't really talk that much about the Burroughs, about that machine. Oh, darn it. When I get excited, the tremor gets worse. Came time to go to graduate school. I went north to Stanford. George Forsyth was a math professor, but he was in the process of starting the computer science department at Stanford, now world famous, of course. So I went there as a math student, but I ended up there 4 years later as a temporary instructor in the new computer science department. We used this machine, a DEC, PDP-1, DEC's first machine. There's a display on that machine, and a guy named Slug Russell from the MIT programmed the world's first video game that we played on that machine. It came time, important event in my life was to the House, was then called the Gatlinburg meeting in Gatlinburg, Tennessee, organized by these 6 guys. That's been a continuing and important event in my life, and the last one, the most recent one, was just a few months ago down at Virginia Tech. So here's all 6 of these guys contributed to MATLAB. Wilkinson, Givens, we have Givens transformations. Forsyth, we have householder transformations. Henrizi and I wrote a paper that I'll tell you about in a minute. And Fritz Bauer from Germany was the principal author of the ALGOL report about international algebraic language, which formed an important part of MATLAB. I wrote a thesis under Forsyth's direction about finite difference methods for eigenvalues of Laplacian. This was the example I used in my thesis, this L-shaped domain. That became the MathWorks logo. And here's how MathWorks logo has evolved over the years as we've added 3 dimensions and color and a lighting model. we're the only company in the world that has the solution to a partial differential equation as our logo. Forsyth and I wrote this book about computer solution of linear algebraic systems based on a course that we both taught. This has code in it in ALGOL and Fortran and PL1 for actually solving linear systems. It was one of the first textbooks to actually have code in it. Here's Wilkinson. Wilkinson used to come to the United States every summer for a short course at the University of Michigan. Then he would go to Argonne Laboratory outside Chicago to visit, to work on this. Wilkinson was doing research on matrix eigenvalue problems. He published his research as programs, as ALGOL code for computing eigenvalues, and these was eventually collected in this book. You can still read this book today. If you want to see how these eigenvalue routines work or see the code for them, go read the ALGOL in this book. It's very readable. But no one could run it because it was ALGOL and nobody had an ALGOL compiler. So Wilkinson was visiting Argonne to help Argonne produce this, IcePack, for Eigensystem Package, which was a project to convert all of Wilkinson's ALGOL to Fortran so people could actually use it. The 6 authors there are from Argonne, and then I visited there in summers. That was followed by the LINPACK project, which was a project to produce Fortran subroutine library for solving linear systems. This is easier mathematically than the eigenvalue problem, but between LINPACK and IcePack, you now had a complete suite of codes for solving dense linear algebra. Here are the authors of LINPACK in 1979, Jack Dungara, who's now a friend of you guys. How many of you know Jack? He's been here. Was a kid back then. There's me with sandals. Jack's LINPACK license plate. And then Pete Stewart and Jim Bunch. Here we are 33 years later. Jack's lost the most hair, but I have the neatest shirt. We took the codes from LINPACK. So LINPACK is now known as a benchmark rather than a subroutine library. And here's why. We took codes from LINPACK and sent them around to universities and national laboratories around the country and asked them to run them, all the codes, just to see that they worked on their machines, and to time one of them. This was a program that solved a 100 by 100 linear system, and you timed it. Dungara penciled in those numbers, which are the megaflops, millions of floating point operations per second. The fastest machine in the world was the new Cray at NCAR in Colorado. It was doing 14 megaflops. The bottom of the list is the machine at Yale. It didn't have enough memory to solve a 100 by 100 linear system. So we had to do a 75 by 75 system and extrapolate. I can't time a 100 by 100 linear system on my laptop today. It happens too fast. But that became the LINPACK benchmark, and it's the basis for the top 500 today. This is still running the LINPACK benchmark, still solving a system of simultaneous linear equations. It's much bigger and it takes longer, but that's deciding the fastest machine in the world. It's really boring because the Chinese build machines maybe to just run the LINPACK benchmark, we're not quite sure, but they're the fastest machines in the world. Here's the one at, I don't know where that is. Now, let me tell you about this. I got time to tell this whole story if I can. Yeah, come here and help me do this mouse so I don't not fiddling with that. I want to get out of PowerPoint, or suspend that, and be prepared to click on this movie here. Yeah. So let me tell you about it first. 1976, I made a film at Los Alamos. I was in New Mexico consulting in Los Alamos. I made a film about computing the singular value decomposition. The SVG was a new thing back then. We had just learned how to compute it from Golub, and I wanted to make a film about computing the singular value decomposition. I also wanted to exercise Los Alamos graphics, and that's what I want to show you here. These were using innovative stuff at Los Alamos at the time. So click on that. I don't want to hear the whole introduction. Well,
to a mathematician,
you're a third of the way through. There, back up. Okay, that's okay.
Matrix analysis can describe the frequency and magnitude of such oscillations. This bridge near Tacoma, Washington, was designed and built
nobody had
before
ever
the effect
seen
of
this
such
piece of
interactions
film
could be
then.
completely analyzed.
You probably, a lot
The
of you
wind
seen it
has
now. This is
reinforced
old
some
hat
undesirable
now, but that was
oscillations with unfortunate results.
innovative stuff.
Modern computers are particularly well suited to solving problems involving large matrices. The designer of a system can obtain accurate predictions about the reaction of his system to external forces.
Now,
The computer
even
is
this
used to
was
simplify
hard
the
back
matrix,
then.
so that
You're
most
about
of
to
the
see
entries
some
will be
Greek letters.
zeros.
Putting Greek letters
One
on the
method is
screen
known as the singular value
was
decomposition.
new stuff then.
The original matrix
You didn't
is
have
represented as
Macs,
the
you
product
didn't
of
have
three
fonts,
matrices.
and
In the second
doing
of these
mathematics on the
matrices,
screen
the only
was
non-zero
new.
elements lie on the diagonal. These elements, the singular values of the matrix, determine the frequencies of oscillation of the original system.
That's not true. They
The
don't
other two
determine
matrices
that.
must preserve the properties
I
of
got
the
it
original
wrong
matrix.
in the script.
So they are
Pete
orthogonal matrices.
Stewart makes me
Each
give
is
that
the product of
disclaimer every
elementary
time I show this
matrices,
film.
which affect only two rows or columns. Scientists at Los Alamos Scientific Laboratory
so here was
have been
using
studying
the
methods
Los
for the
Alamos
accurate and
graphics
efficient
library.
calculation of the singular value
Computing these
decomposition
intersections of
and of
these
describing to
pyramids
computer users
was
how the
hard. That
computation
was
is
a
carried
hidden
out.
line algorithm
In this
then.
three-dimensional
This was before
representation of a small
Z-buffer
matrix,
and
each
the
pyramid
way we do it
depicts the
today.
magnitude of a
So
single
I'm
matrix
going to try
element.
and show you how the
The
singular
diagonal
value
of the matrix
decomposition is
runs from the
computed.
upper left to the lower right. Orthogonal transformations will be used to introduce zeros into the matrix.
So it used to be
The
in
initial
Fortran.
transformations put
You
zeros
would read
into the
from
first
Unit
row
5,
and then the first
write
column.
to Unit 6.
Each transformation
But if you, Los
affects two
Alamos, if
other
you wrote
columns
to
or
Unit
rows,
7,
shown here in blue.
they shipped it down to
Later
the basement and made
transformations
film
introduce
out
zeros
of it.
into later
So
rows
they
and
were
columns,
doing,
while
this
preserving the
was
zeros already obtained.
16 millimeter celluloid film
It is
that
not
I'd get back
possible
in
to
my
annihilate all
box,
the
output
off-diagonal
box the
elements
next
in a
morning.
column. So this first stage
So I made this
produces a
film
matrix
doing that
with
stuff.
non-zero elements directly
Anyway,
below the diagonal, as well as elements. But the changes
If you
are
really
not
want to know
visible
how the
on this
SVD
scale.
is computed, you can
Once
go
a
to
few of the
YouTube
singular
today
values have been
and
obtained,
type
the
in Molar
off-diagonal elements have
SVD
become
and
so
watch the
small
whole film.
that each of
It's
the
kind of fun
remaining
to watch
singular
it.
values is obtained with a single iteration.
Maybe I can, okay, yeah. Yeah, now
The final
the
diagonal matrix,
okay,
together with the two
just get out of
transforming matrices.
that. So in a couple years later, the producers of the first Star Trek movie came to Los Alamos to get graphics to run on there. Now I'm going to keep the lights down because I'm going to show another piece of film. They wanted to get graphics to run in the background on the bridge on the Enterprise, and so they got graphics from Los Alamos. And I'm going to take this film. This is a clip out of the first. Yeah, get it as dark as you can now. I think I can get this. This is out of the first ever Star Trek movie. Look over Spock's shoulder. So, throughout the movie, the singular value decomposition is being computed on Spock's screen.
Just enough for us to break free.
Break free to where, Commander?
This would be huge, Captain. We don't know that, Mr. Spock. Why are you opposed to trying?
And there's real graphics there. We're just about finished with this, yeah. Okay. One last little bit. V'ger is threatening the universe, and they're going in to find V'ger. If any of you have ever seen this, remember this film.
Why bring us inside? Not to destroy us. They could have done that outside.
They still can. Curiosity, Mr. Decker. Insatiable curiosity.
There's a tagline for Ski Institute there. The curiosity, insatiable curiosity. Okay, so that was the first Star Trek movie. And this is what it was doing. Here's it showing that thing again, diagonalizing the matrix. I was teaching numerical analysis and linear algebra, thanks, at the University of New Mexico. I wanted to have my students use LinPack and IcePack without writing Fortran programs. So I read this book by Klaus Wirth. He invented Pascal, and he had a simplified version of Pascal here called PL0. And this was how to parse programming languages to generate code for PL0. So I wrote MATLAB in Fortran at this time, and with PL0 with matrix as the only data type. It's a strongly typed language. It had only one type, and that was the first version of MATLAB. Here's a screenshot of the first version. This was back in 1981. If you said help, there was a list of these functions. This is all the functions. There weren't M files. There weren't toolboxes. There's no ordinary differential equations. There's no FFT. If you wanted to add functions, you'd get the Fortran source code from me, write new subroutines in Fortran, and add them to the parse table to expand this list. Here's what some of the things you could do. This was a joke about what graphics was like. This was portable machine independent graphics in the 1970s. 1979, I visited Stanford on a sabbatical. I taught a numerical analysis course, graduate course in numerical analysis. Half the students were math and computer science. They weren't impressed. I used this MATLAB, among other things. And this was not a sophisticated programming language. It wasn't a programming language, it was just a calculator. It wasn't sophisticated numerical analysis research. But the other half of the students were from engineering, and they loved MATLAB. They were doing things that I didn't know anything about. Control theory and signal processing. And matrices was the language for these system theory that they studied. And they wrote programs in MATLAB. They went off to a couple of companies that had spun off the Stanford EE department, They were in Palo Alto. They were doing control theory on contracts to the Air Force. One was ISI. They built something called Matrix X on top of my MATLAB with my permission, and that became a product of theirs. Matrix X ended up being a competitor for MATLAB for years to come. Crosstown at System Control Technology, they built a package called Control C, one of the great all-time names for a piece of software. And a guy named Jack Little was the principal developer of Control C. He hadn't taken my course, but a friend of his had, and he showed Jack MATLAB, and Jack threw away all his Fortran and started using MATLAB. He came to me a couple years later and said he wanted to start a software company. So I said, great, go ahead, good luck. And he disappeared into the hills behind Stanford, quit his job at SCT, spent a year and a half reprogramming MATLAB in C, which was a gutsy thing to do back then because C had never been used for a large-scale technical program like this. He had a friend named Steve Bangert, helped him work on that. And the three of us, Jack used this machine. The PC had just come out. Jack went down to Sears and with his own money bought a compact portable and used this machine. At first he didn't even have a hard drive. He had to put floppies in and out. And the three of us founded MathWorks in California in 1984. There was the software had not been written with the idea of starting a company. These people, the people in control theory, found it useful. And Jack started the company. He was the only employee the first year. We had 2 to the 0 people. The next year, Bangert went to work for the company. We had 2 to the 1 people. And the company developed it, doubled every year for the next 7 years. Here's a log plot of the size of MathWorks over the last 30 plus years. We haven't continued to double every year, which is a good thing. Otherwise, we'd have 2 to the 34th people. And worse yet, we'd have to hire another 2 to the 34th in the next year. Here we were when we had 2 to the 3 people. There's 8 people in South Natick. Jack's down in the front row. Lauren Shore up there on the left side of the picture still works for us, and so does Jim Tung. I didn't work for the company for the first 5 years. I went off to try and find my fortune in Silicon Valley, but that's a whole other story. In 1989, I gave up Silicon Valley, or they gave me up, and I joined MathWorks full time. Here's 2 to the 5th people, and I'm over here on the left, and here's Jack. Boy, that sure is tremoring. And there's Jack on the upper right. Here was a couple of pictures in San Diego a couple years ago when we had our 30th anniversary. We had 3,000 people then. So MathWorks today has about 4,000 people. It has offices at more than 20 places around the world. Most of these are sales and support offices, but there is some development done in Cambridge, England, in Edinburgh, Scotland, and Paderborn, Germany, and in India. But most of it is done here. This is our campus off of Route 9 in Natick, Massachusetts, about 15 miles west of downtown Boston, near the Massachusetts Turnpike. Now, this is an important slide, but I'm not going to talk about it very much. MATLAB is way beyond matrix laboratory today. On the list of most popular programming languages is the IEEE publishes. We're number 7th or 8th after C and Java and Python and R. But we're gone beyond matrix laboratory, and we're used in a wide range of industries. There's what is that in the upper left? What is that up in the upper right, Orly? DNA molecule. We're into bio stuff. Here's I can't point to those things. There's a hearing aid. My wife was looking for a hearing aid for her mother. She says, hey, Cleve, here's a MATLAB plot. Sure enough, they had a MATLAB plot on their homepage. There's about a dozen hearing aid companies in the world, and all of them use MATLAB for development. In the center at the bottom is image processing, a car driving at dusk in a stormy night, in motion, trying to read the license plate number. Chips and circuits in the right, lab equipment. On the top represents our principal business, which is control theory. So programming that vehicle is a delicate control theory problem. You simulate the quadcopter on a computer screen, the people doing it, and then generate the code that controls it and download it into the device. In the center is the Chevrolet Volt. There's something like 4 dozen microprocessors in the Volt, and they're all programmed using MATLAB. Again, the engineers doing that sit at computer consoles like all the rest of us, run simulations of the part they're developing, and then download the code that drives that car into the microprocessor, which goes in the Volt. So MATLAB doesn't run in your car, but code generated by MATLAB does. The same is true of the satellite that flew past Pluto a couple months ago. I'm not sure about Cassini. I got to find out what was happening in Cassini, but I do know that the one that went by Pluto was code generated by MATLAB. They sit at consoles. This is in Hopkins or someplace that's by Maryland. Simulate what they want to do with the satellite, generate control code, and then send that control code to the satellite. It takes 8 minutes to get there. You talk about latency. And the damn well better be right? Because they don't get to test it. Anyway, so that's how we make a living, is doing all these kinds of things. I've got, let's see. I'll show this. This is fun. This is work by Nicholas Troji who was in Germany, is now in Canada. You can go to the webpage called Biomotion Lab and see this work. He's interested in the human gait, particularly how we as humans recognize what other people are like by watching them walk. You see somebody walk? Is he sad, happy? Is he male? Is she female? How do we know that from the walk? So he puts his graduate students on the treadmill with markers on them and follows these markers as they walk. That produces, captures about dozen seconds of the walk, couple dozen steps, That's a couple thousand frames. There are 15 markers on the body, or he follows 15 markers, and they are move in 3 dimensions. So you get these time series, 45 of them, that show what the subject is walking. The raw data is a matrix with 45 rows and a couple thousand columns. Here's what the signal looked like. You can see this periodic motion of these various steps as they're walking along, and he wants to do model reduction and get out the essence of that walk. Here's when you zoom in on what the signal looks like. His model is 5 terms of a Fourier series, with the only nonlinear parameter is omega, the frequency. He finds that by the Fourier analysis. And then he computes 5 vectors. These are the principal components of that walk. He's using its SVD. Orly was showing me some work earlier today about how she's using the SVD to do far more sophisticated stuff and more life-important stuff than this in cancer research. But that takes and reduces the thousands of columns of the matrix down to 5. These 5 vectors that represent the 5 coefficients in this Fourier series. He then takes all the walkers. So he gets 5 components for each walker. Then they're half female and half male. The 5 components don't come out to be gender. You can't tell the gender from the first 5 components. But he takes half the subjects are female, half are male, and he computes singular values of the males and singular values of the females. That's 2 different matrices, M and F. And then he adds those 2 together, takes the average of those. That's a universal walker, common man, an eigenwalker. And the difference between those 2 is the gender. So let me show you, that's all the slides I've got. So let me show you that app. I hadn't brought that up front. Oh, this is not the right one. Okay, I found it. So here's 6 of the subjects. Right? This is not actual data. It's their 5 vectors in the Fourier series, but this gets about 95, 97% of their walking. So you can see different personalities here as we go through these guys. Now, poor Jamie here is having a bad day. But how do we know that? What is it about Jamie's gait that tells you he's having a bad day? How do you recognize that right away? Let me get to my 2 favorites here. Pablo and Patricia here in the. All right, so those are extremes of these 2. All right, so when you combine all that, you get the eigenwalker. And here's the typical walker. There are these components, the principal components here. If I just take, let me remember how I did this. Oh, I wanted, there's supposed to be, if I reduce the magnitude of these things, you get, this is just something called stride, we call stride. Add to that some sway, and then some motion that's in phase with the upper body and lower body are in phase, and then here they are out of phase, and we get somebody that walks, somebody that looks pretty good walking. But as I said, gender isn't in these 5 components. So here's a gender button. Now, can you tell which gender that is? Pixar and Disney long ago knew that you had to overemphasize these things in animations. So let's move that coefficient up by a factor of 3. Now you can recognize the gender. I didn't tell you which it is, but we all see what it is. How do we know that? And then let's go over here to the male. It's in the elbows that we see gender. Okay. So that's just a fun thing that I love to show. And it's singular value decomposition. It's numerical linear algebra is underlying that demo. It's the same tool that Spock was using to find V'ger. Okay. So even with the version for the burrows, I've got, I want to make, I'll talk something about HPC. If it's I think it's back down here on the, so let me just go right to this. So we have a parallel computing toolbox. It runs on big computers. I don't think you have it on your big computer here. Most people, I mean, we're not in the high performance computing business. We're in supercomputing for everybody else. We're not trying to do the top 500. And most of the parallel computing toolbox is used in this way. Let me go. Oh, okay. I was with this Intel-based startup in Oregon that built the first parallel computer, that was one of the hypercube. We had a conference on hypercubes in Tennessee. Here's from out of the proceedings. And I'm the guy who invented embarrassingly parallel. Embarrassingly parallel means that it's just a bunch of independent processes running It was a parameter sweep or Monte Carlo, something like that. The machine ran on 220 volts. We didn't have 220 volts in the parlor at the hotel where we had the machine, so we went out and rented a gas generator and ran a cord across the swimming pool to get into the parlor to run the machine. When I gave a talk about the machine, somebody asked me how many megaflops per gallon are you getting? Well, that's important today, right? That's the big question facing high performance computing is how much energy are you using? Is as important as how many megaflops you're getting. But most of the parallel computing toolbox has a parallel for loop, par 4. Par pool initiates the use of multiple copies of MATLAB. Par 4 runs a bunch of independent loops. And then there are other things like SPMD and where you can do more sophisticated parallel computing. But most of the work is being done like this. When you came in, I was playing blackjack. Maybe you saw some of that. There's an old blackjack program that I wrote years ago that simulates the game of blackjack and the best strategy for blackjack. Not card counting, but just playing blackjack and seeing what the dealer's card is. The statistics of the blackjack, this is a financial instrument. This is like simulating the stock market or options prices. Some of the same statistics. So this is a stand-in for those. So this program plays 4 players playing 10,000 hands of blackjack. And the par 4 says these 4 calls blackjack, which is this program I wrote years ago that plays blackjack, and it calls them 4 times with independent starting random number seeds. That's a whole important story. But then collects the results together. Now, I want you to look at the array B. Where does B live? This program runs on a front end, a master, and it sets up B. But each of the 4 workers has to put something into B, and then finally we plot it, and we get this plot. So blue did pretty well. The 2 colors there in the middle did middling, and then the purple lost money. But in this run, we came out a little bit ahead over these 40,000 hands of blackjack. That's a typical kind of simulation that's done with parallel MATLAB. If I run that on my laptop has 2 cores. If I run it just without saying par pool, it takes 8 seconds. And when I start up 2 more MATLABs, each of them simulates 2 players, the thing takes 4 seconds. So there's linear speed up on this embarrassingly parallel, almost. It's not quite embarrassingly parallel because that array B collects the results together. And there's some, if this is on a distributed memory cluster, there's some MPI going on underneath to get the results back and forth between the master and the workers. Okay, that's it on parallel computing. Let me summarize here. MATLAB's historical and intellectual basis is in numerical linear algebra, but we'll go way beyond that today. and its commercial success is based in technical computing. Nevertheless, it's still based on mathematics. So this quote from Jim McClellan at Georgia Tech says, MATLAB wasn't designed to do X, but it can do it because it's based on mathematics. And some principles of some ideas from computing, like processing arrays and using that notation to do arrays. Okay, that's it for. Thank you all for coming. Thank you for standing up for this whole time. If you're in the peanut gallery here, I enjoy coming back to Salt Lake, and we should do it. It was 10 years ago before I was here before. We should do it before. I'll give a different talk then too.
You go for a question or two?
Yeah, absolutely. As much time as you guys want.
Question for Cleve?
Did you have a slide about why the semicolon's not used or something? I teach MATLAB and we always talk about the semicolon. I thought I saw a slide.
But the semicolon slide.
Maybe I misread it.
There was a slide about why there isn't a parallel MATLAB. That was one of my most widely cited papers years ago, but then we came out with a parallel MATLAB. The reason why years ago there wasn't a parallel MATLAB is because the memory model was wrong. We used to think of distributing arrays and doing linear algebra on arrays that were distributed across multiple machines, because we didn't have as much memory on a single machine. But now these machines have so much memory that you can do all the linear algebra you want on one machine, and you don't need to use the distributed array. Partial differential equations are a different story, but I don't remember anything about semicolon. No, nobody ever asked me that before. Yes, in the back. I'm surprised that wasn't the first question. So did you all hear that? What about open source, Octave, and Python? Sure, that's a very important consideration for our company. We try and explain why open source doesn't mean free. You still have to spend money, even though you didn't pay anything for the software. And the support MathWorks supplies. One of our biggest customers is Toyota. They use it to design their automobiles. I don't think they would consider using Python because they don't have any support particularly, or if there is support, they have to pay for it. Python is not numerical linear algebra. It's a broader scripting language, and it's very popular. R is popular in the biomedical community. So this is a competitive concern for us. What we're trying to do about it, but some who I was talking to before about here this morning, who was just frustrated with the MATLAB licensing and tried to use MATLAB on the airplane, but couldn't get access to your license server. So it doesn't have to be that way. We have ways of selling MATLAB to universities now, where all the faculty and all the students can use it without having to access a license server. So we do things like that to make it easier to install on an individual machine, and easier to get access to the necessary licenses.
Any questions for Cleve? Yes, Mac. Rich,
Yeah, APL stands for A Programming Language. It was a book that Ken Iverson from IBM Research, he used it in a book. His intention was to be able to describe algorithms in this language, and he didn't think of it just like Matt. He didn't think of it as necessarily implementing it as programming. As a programming tool. And then other people at IBM Research implemented it, and it was available on IBM machines years ago. It's an array language, but I knew about it, but the syntax is awful. It's really cryptic. It's elegant, but really cryptic. One of my graduate students walked in my office one day and showed me this line of gibberish and says, "Hey, Cleve, look at this." And I says, "What's that?" He says, "It's your algorithm." I says, "My algorithm for what?" It was an APL program that I couldn't read. I had no idea what it was doing. The character set was idiosyncratic. So an array programming language was a good idea. I used to say that MATLAB was APL, portable APL with a civilized syntax. There was another thing called Speakeasy, developed at Argonne by a guy named Stan Cohen. That was another array programming language that I was aware of and that I had used a bit. So these things were in the air back then, and certainly influenced my thinking.
All right, let's thank Cleve for a really interesting talk. Thank you for